Hi friends, this is Kruti Jai Pancholi, Assistant Professor in LJ Institute of Engineering and Technology in Department of Electronics and Communication. This video is about subject Analog and Digital Communication Systems. In this video, you will learn about the examples related to the Parseval's energy and power theorem, energy spectral density, properties of energy spectral density, and the example based on the ESD. As we have learned in the last video about what is the energy signal, what is the power signal. So now in this video we are going to first of all solve the example related to that. The example is find the energy and verify Parseval's theorem for the energy signal xt is equal to e raised to minus 4t ut. The simple way we can find out the energy by using the equation E is equal to minus infinity to infinity x square t dt. For the real valued function, we can take the modulus of this. So it is minus infinity to infinity modulus of xt square dt. But here we have what is the xt? Xt is e raised to minus 4t ut. So we are putting the value of the xt over here and the square of this and dt. Now we know that ut is the unit step function. Unit step function, that is ut is equal to 1 for the t greater than 0 and ut is equal to 0 for all other values. So here we can change the limit from 0 to infinity to get the ut is equal to 1. So now I will change the value of the limit, okay, and I am not putting the ut equal to 1. Simply we are understanding that the ut equal to 1. So here you can see that it is 0 to infinity e raised to minus 8t dt. So e raised to minus 4t ut equal to 1 we are putting. So over here it is e raised to minus 8t. So e raised to minus 8t. Okay. So here e raised to minus 4t square. Okay. So don't do the 4 square. But while such kind of the things is there, it is always multiplied with this. Thus it is e raised to minus 8t. So now we will take the integration of this. So it is e raised to minus 8t integration is e raised to minus 8t upon minus 8, 0 to infinity. Now put the value of the t inside this. So we are putting the limits. So it is 0 e raised to minus infinity, okay, plus minus minus plus, okay, e raised to minus infinity. Here it is what? 0. But we are putting the limit, that is minus, here minus, so minus minus plus, so it is 1 upon 8 e raised to 0, so e raised to infinity is 0 and this answer is 1 by 8. So simple way you can find out the energy of the function, that is the e raised to minus 4t ut, it is 1 by 8 joule. Now again, we know about that whenever the e raised to minus 80 ut function is there, it's an energy signal, and the energy signal having the energy, it's always 1 upon 2a. So in the multiple choice question, while the question can be asked that what is the energy for e raised to minus 4t ut function? So you have to find out the answer simply by considering this. It is 1 upon 2a. So 1 upon 2 multiplied by a is equal to 4 and it is 1 upon 8j. So this is the one way we have verified the answer. It is 1 by 8j. This is the another way you can say that the energy is 1 by 8j. Now we want to verify using the Parseval's theorem. So in the Parseval's theorem, what I said earlier, that the equation, okay, for the Parseval's theorem, that is, in the time domain, if the signal is available, then we can find out the energy of that signal also. But sometimes the time domain representation of the signal is very complex. Then it is mandatory to convert the time domain signal into the frequency domain. So now whenever it is in the frequency domain, again using the Parseval's theorem, we can find out the energy of the signal. So it is E is equal to 1 by 2 pi in integration of minus infinity to infinity modulus of x of omega square d omega. X omega is what? It's a x omega is the spectrum and this is the square of the spectrum. So we know that the Fourier transform of xt signal is x omega. Here what is my xt signal? It's a e raised to minus at ut. So e raised to minus at ut function is there. Then the Fourier transform is 1 upon a plus j omega. So we need a modulus of x omega. So we can write the 1 upon modulus of 4 plus j omega. And this is the complex functions. So what we are doing? We are doing the square of that. So it is the modulus of x omega square. It is equal to 1 upon square root of 4 square plus omega square. So now we are putting this value in the equation. It is E is equal to 1 by 2 pi integration of minus infinity to infinity. What is my modulus of x of omega square? It's a 1 upon 4 plus omega square d omega. Okay, so it is the function. Now we know that if it is a minus infinity to infinity, a square upon a square plus omega square d omega, then it is tan inverse omega upon a. So now it is what? Okay, now I need to convert the equation form into this form. Here we need a square. So what I should do? I should multiply and divide by the 4. So it is 1 upon 4 multiplied by 2 pi integration of minus infinity to infinity 4 upon 4 plus omega square d omega. So now we are putting this particular function over here, that minus infinity to infinity 4 upon 4 plus omega square, that can be represented by what? Tan inverse omega upon a. So it is tan inverse omega upon 2. Limit is minus infinity to infinity. So we are putting tan inverse infinity by 2 minus plus tan inverse minus infinity by 2. So here we know that tan pi by 2 is infinity. Tan pi by 2 is infinity and tan minus pi by 2 is minus infinity. So tan inverse infinity is equal to pi by 2 and tan inverse minus infinity is minus pi by 2. So now we are putting the limits. So it is 1 upon h pi tan inverse infinity minus tan inverse minus infinity. So it is 1 upon h pi, but what is tan inverse infinity? It's pi by 2 minus tan inverse minus infinity is minus pi by 2. So it is minus pi by 2. It is equal to 1 upon 2 h pi. It is pi minus plus. So it is 2 pi divided by 2. So it is the 2 is cancelled. Pi is cancelled. And answer is 1 by 8j. So we can say that we can verify the Parseval's theorem. Okay, using that. Okay, answer is the 1 by 8 joule. Okay, so we can say that if the signals are available in the time domain, in the frequency domain, we can find out the energy resides with the spectrum using the Parseval's theorem. So this way you can solve the other examples. Okay. Now next, Rayleigh energy theorem. Now this Rayleigh energy theorem, that is again another analogous to the Parseval's power theorem. So it states that the total energy of the signal xt is equal to the sum of energies of its individual spectral components in the frequency domain. So what we can say, that the total normalized energy of a signal xt is given by E is equal to minus infinitive to infinitive modulus of xt whole square dt. According to the Rayleigh energy theorem, total normalized energy E is equal to minus infinitive to infinitive modulus of x f square df. So this way we can say that the normalized energy is equal to the area under the signal corresponding to the square of the amplitude spectrum xf of the signal. In this section, we will learn about spectral density function. What is a spectral density of a signal? It is the distribution of the energy or power per unit bandwidth as a function of a frequency. The spectral density of energy signals is called energy spectral density, while the spectral density of a power signal is called power spectral density PSD. Now in this video we will learn about energy spectral density. We know that our signal xt, then the Fourier transform of my xt signal is xf, and the xf amplitude spectrum square is a xf square. So it is defined as the energy spectral density. So energy spectral density of xt function is denoted by psi f. So what is the energy spectral density? It is whatever the signal, then the spectrum of that signal, and the squared amplitude spectrum of that signal is the energy density spectrum. So it is the ESD is equal to the psi of f is equal to modulus of x of f whole square. It also measures the signal energy distribution across frequency. Now we'll learn about the properties of the energy spectral density one by one. Now the first property is the energy spectral density of an energy signal xt is a non-negative real valued function of a frequency. Mean always your psi f value that is greater or equal than 0. Why it is greater or equal than 0? Because over here we are doing the modulus of x of f and the square of that. So it always gives us the positive value. Property number 2. It's the ESD of a real valued energy function xt is an even function of frequency. Mean you are taking the positive value of the f or minus value or negative value of the f, the spectrum value, that is always the real valued signal. So it's a x of f is equal to the modulus of x of minus f. So now we are doing the square of that. It's nothing but it's a psi of f. So it's a modulus of x of f square. It's a energy spectral density of this function. It's a psi of f. Modulus of x of minus f whole square. It's a psi of minus f. Property number 3. total area under the curve of ESD of an energy signal xt is equal to the signal energy, mean area under the particular spectrum, that is the energy spectral density. So now we'll see the proof of this. Then I know that what is my normalized energy equation? E is equal to the area under psi f. Now area under psi f mean it is equal to minus infinitive to infinitive psi of f df. But what is this psi of f? Psi of f is the energy spectral density of suppose function modulus of x of f whole square. So it is minus infinitive to infinitive psi of f df. But what is psi of f? Put the value of the psi of f over here. So it is the psi of f is equal to modulus of x of f square df. But what is this? So according to the Rayleigh theorem, this is the energy. So I can say that area under psi of f, area under psi of f is equal to the signal energy E. So this is the property. Now the next property, property number 4 is when the energy signal xt is passed through a linear time invariant system. So you have the signal xt passing through the LTI system, having the some impulse response and producing the some response or the output signal, which is equal to the product of energy spectral density of the input, energy spectral density of the input and squared amplitude response of the system. So we'll draw the diagram. This is my LTI system. This LTI system having the one input, that is the xt, having the one output, it's a yt, and this system having the impulse response is ht. So what I can say, what is my yt? Yt signal is xt multiply with the ht. Okay, so you know that when the signal it is in the time domain, okay, what we are doing? We are taking the convolution of the two signal. So it is the yt is equal to xt input signal convolve with the ht. So here xt is the input, yt is the output, ht is the impulse response of LTI system, and yt is equal to xt convolve with the ht. Applying the Fourier transform in this equation, the Fourier transform of yt is y of f, Fourier transform of xt is x of f. It is the convolution, but while it is in the frequency domain, it is the multiplication sign. ht, the Fourier transform of ht is h of f. So important notice, convolution in the time domain gets transformed into multiplication of transforms in the frequency domain. So now we'll take the square on both the side of the equation. So it is modulus of y of f square is equal to modulus of h of f whole square into modulus of x of f whole square. What is this y of f square? It's a energy spectral density at the output end. So it is psi 0f, 0, not 0, but it's the indication of output, equal to modulus of h of f square into psi if. What is psi if? It's a modulus of x of f whole square. It's a ESD of input xt. Property number 5. For an energy signal xt, the autocorrelation function and energy spectral density form a Fourier transform pair. Autocorrelation means the correlation of the function with itself. So it is denoted by the R tau, and the Fourier transform of that provides you the psi of f. We will study in the other chapter about the autocorrelation. So right now you have to keep in mind only this thing. Now we'll solve the examples based on this. A filter has an input xt equal to e raised to minus t ut, and impulse response ht is equal to e raised to minus 2t ut. Find ESD of output. The solution is, what is my equation as you have studied earlier about it? LTI system having the input xt, output yt, the system having the impulse response ht. So I said that yt is equal to xt convolution with the ht. Over here we need to find out the ESD. So output ESD is equal to the square of the amplitude spectrum of this impulse response, it is modulus of h omega square, into input of ESD. Input of ESD is what? It's a input of ESD, that is the ESD of this function. So we know that what is the spectral density? Spectral density, that is the amplitude spectrum whole square. So in input spectral density, that is input function is xt, the Fourier transform of xt is x omega, and spectrum density, so it's a modulus of x of omega whole square. But we know that what is my xt? Xt is e raised to minus t ut. So we know that the Fourier transform of xt is x omega, and e raised to minus t ut, the Fourier transform is 1 upon a plus j omega. So now we are putting the value of that is modulus of x of omega equal to 1 upon modulus of 1 plus j omega. It is equal to 1 upon square root of 1 plus omega square. So the h of omega now, it is Fourier transform of ht. What is ht? It's e raised to minus 2t ut. Similarly, we can write down the Fourier transform of that. It is 1 upon modulus of 2 plus j omega. It is equal to 1 upon square root of 4 plus omega square. And therefore, the square of this is 1 upon 4 plus omega square. So now I am having the value of the modulus of h omega square, and I am having the value of the input spectral density x of omega square. Okay, that is this. So now we are putting all the values in the equation. Therefore, the output energy spectral density is equal to modulus of h omega square into input ESD. So now putting all that value, you will get the output spectral density. It is equal to 1 upon 4 plus omega square into 1 upon 1 plus omega square. So while you have the signal like this, that is the xt is equal to e raised to minus t ut, and ht is equal to e raised to minus 2t ut, you can have the ESD at the output is 1 upon 4 plus omega square into 1 plus omega square. So this is the last point of this video. Thank you very much, everyone.